So I guess you kind of picked up last time I was big on nuclear power, okay, and pushing for that, but we're really using that to generate heat or steam, which then we spin a turbine and generate electricity, because the main goal, again, to produce power at scale would be through electricity. So in terms of the actual nuclear reactions and so on, it's really hard to conceptualize how we would use that in any other way other than making things hot. So here now, in this lecture, I'll compare ways of generating electricity, ways of storing electricity. So since that's the, I wouldn't say it's the most portable. Well, I guess it depends. You know, for small power requirements, it is. You have these little batteries in your phone and so on. So in that respect, it's the most portable. But if you need higher powers than that and less weight than that, you can go back to the QSPR lab. And it's really hard to beat fossil fuels, gasoline, you know, because those motors can generate power at a moment's notice, and you can turn them off and it sits there and your gas tank isn't lossy. The fuel doesn't disappear, you know, whereas a lot of electrical systems are lossy. So let's talk about electrical sources and storage technologies. And this is really just a survey of what I found online to kind of give you an idea of the power grid and how we deal with that, and then personal electronics, like the full spectrum. So this is there'll be a few things in here that are on the homework, but for the most part, this is just sort of helping you expand your knowledge about the society you live in and how we generate electricity. So there's different sources of electricity. Obviously, the redox reactions, we can use those to generate batteries. So we can push electrons through circuits by using dissimilar metals or other kinds, sometimes oxygen. We can use electromagnetism. Haven't really found a good way to do this except through solar cells. You can bring in, you know, light and split a nucleus and an electron and send the electron through your circuit. So you can use electromagnetic radiation to generate electricity, and those would be photovoltaics. And then how do we store it? Well, short-term, long-term storage, we need to discuss what is involved in those things, you know, and whether we need power versus energy. Low impedance and high impedance. So impedance is sort of the resistance to flow. So if you're trying to pull electrons out of a battery or out of a circuit, it's the resistance to delivery. Trying to think about it. Think about your energy being in a funnel, and this is the size of the hole coming out of that funnel. So that's impedance. It's different than resistance. Resistance is the resistance of electrons flowing through a circuit. So we don't really think about the impedance we typically use for sources of power. And so if we have a really low impedance, it can deliver a lot of amps. Like a car battery is 360 amps. It'll deliver a lot of current. And so that's a very low impedance thing. Whereas some of our like regular old alkaline batteries, they have a higher impedance. They don't deliver that kind of current. Okay. And then lossless versus lossy storage. So lossy is the word that we used in graduate school. So I kind of looked that up and think, is that a real word or whatever? And so, yeah, it's a process or storage medium that loses material or information. Okay, we call it lossy. So I looked up the Urban Dictionary, and it's not that definition. So, so in this respect, I'm talking about something that loses things over time. So your batteries in your shelf, you know, you buy a bunch of batteries, and over time they will lose 1 or 2% of their charge every week. They're lossy. Okay, so that's a problem. You can't store up your energy in a bunch of alkaline batteries and come back 10 years later and expect them to be ready to go. Okay. And so this is the main chart that we're going to be using today. This is all of the different sources and conversions, and sinks, places where we use energy. And I've added this one over here because we're going to be talking about compressed gas storage. So this one here is a new leg on our chart. So gravity and compressed gases. So we can store energy. It's typically a storage medium, but it's also hydroelectric. Like the rainfall lands uphill and is rolling downhill through the rivers, lakes, and streams, and we can dam that up, and so now we have gravity, and we can turn that gravity into electricity. And so that's where hydroelectric comes from. We could also stuff gas into a container or a geologic formation and have that at high pressure, and also then use that to spin a turbine. So we've added that piece. This is our overall electrical landscape, I guess, in the United States. This is from 2002. I keep this old one in here just to show you several things. One is that we use about, like I said, about a fourth of the primary use of energy here. So 115 exajoules per year, and the globe or world is 425, or was at that time. Okay. And then this is the net efficiencies for all the different sectors of our economy. So all of these primary uses, so into our electrical power sector, we have some electrical imports from Canada and places like that. We have nuclear power stations, hydroelectric. We do have apparently some biomass that we feed into our power grid. Some of that may be from like paper pulping. So we squeeze the paper, like the wood chips and so on, and try to get those lignins out. And some of those heavy aromatic compounds, we really don't have a use for it just yet. And so they can feed that into oil-fired power plants, natural gas, and then coal. And then a little bit of petroleum. So that's our energy mix for our electrical power grid in 2002. These numbers come from Lawrence Livermore National Laboratory and Energy Information Administration. And so look at the overall efficiency. This is how much electricity we distributed. So 12.5 exajoules, and then we lost 27.8. So that's about a 31% efficient. So that's crazy if you think about that. That's of 100 joules coming in to the power plant, only 31 got distributed to the end user. And this is probably best in class, like best in the world. Okay, so this, I mean, we have the money and the resources to try to do it the best way possible, and we're still only squeezing 31 joules of electricity out of all of these primary sources. Residential is a little bit better, because we can engineer our homes and control things quite a bit better. So we're coming in at residential 15 delivered over 20 taken in, so that's 75% efficient. Industry here in 2002 was good at 80%. So again, they lost 4 out of 20 joules, so 80%. The non-fuel uses, that again is like lubrication, motor oil, and greases. And then down here, transportation. So they brought in 27 and used 5.6, so about 20% efficient in transportation. A lot of room for growth and efficiency in transportation. Now, I don't exactly know how they calculate that. It would be interesting to know how they calculate how efficient transportation is. Now, we can calculate the motor, how efficient the motor is, and gas engines and diesel engines are about 25 to 35% efficient. And so, how are they calculating the efficiency of getting you from A to B? Right? One of the, I guess, probably the best efficiency gains now is it was implemented in several modern cars, mostly smaller cars. My sister's car in particular, she had a little Volkswagen, and we're driving in Austin, and I was driving her car, and we're in a really infield road, really busy road, and I pull into the left lane at a red light, and how you kind of pull into the intersection so that when it turns red and everybody stops, you can exit, because it's really hard because there's never break in traffic. I get out in the middle of this intersection, which is 5-6 lanes going in all directions, and the car shuts off. I was like, cow, what am I going to do? Like died on me. And I was like, oh my gosh. And she said, what? And I said, your car died. And she goes, oh, it does that. Every time you stop, the engine turns off. Yeah. And you let off the gas and it starts up. or let off the brake. You put on the brake, engine cuts off. Have y'all seen this before? Oh my gosh, that drives me crazy. Because in my car, when I was in high school, I had a beater, like Mercury Monarch, canary yellow with the rusted hail dents. It was a sight. Oh man, if that thing died, you were not guaranteed to get it started again. And so that panic, I'm in the middle of a busy intersection in Austin, Texas. And I mean, it was reliable, but that was great because I'm not burning gas sitting still. So there's some really, that's a simple solution, but you got to have a reliable starter. And I bet that starters, maybe they've made them better, but I can imagine that thing wearing out eventually. Not really. No, you may crank it. A lot of people say that, it costs so much gas to start it up that they'll run their vehicle for a long period of time. We used to have a diesel truck that would park up here in Farrington when we were in that building, and they just left their diesel running all day. It was so stupid. That's like this urban legend. Oh, it costs so much to start it. It may maybe for like a small period of time, like seconds, I would imagine. But once over seconds, you've recovered from that little burst of fuel, that because it doesn't spray a lot of fuel into those cylinders to get it started. So there may be a kernel of truth to that at a really short time frame, but minutes, no. I think it's shut your engine off and you'll save a lot. Okay, so then 2019, I updated this in 2021 to kind of see what happened in 2019 and 2020 because COVID. Okay, we shut down the economy. So this is 2019, right before COVID. What happened from 2002 to 2019? We dropped our energy usage, our primary usage, by 12 exajoules, which is not a small amount. That is huge. It's almost 10%. And yet we still produced less useful energy, but we also consumed. Yeah, so our percentage, let's see, what do we have here? Let's calculate this. Get your calculators out. I want to see what this was. I didn't have this number on here. So we have on the bottom 59.3 plus 37. I think that's should be 115 exajoules, 37.1. Let's see. No, it's not. And then we put the 37.1 on top. So someone calculate that percentage, if you would. Yeah, so this is strange. 38% efficient in 2002. We dropped to 33% efficient in 2019, but we consumed less energy. I was thinking that we consumed less energy because we got more efficient, but there's some differences there. But anyway, the point was we dropped 12 exajoules in 2019. Look what happened in 2020, 92.9. Again, that's a huge drop. In terms of magnitude, like another 8 exajoules drop. But think about what we had to do to get that extra 8. We shut down all kinds of things, producing less energy. We're at 33%, so we maintained the same percentage of efficiency as 2019, but dropped in our consumption and dropped in what we produced. Okay. So if we think that we're going to conserve our way out of using all of this energy, think about the disruption in our lifestyles. So that's, I guess, the take-home lesson of looking at our energy mix. We shut down economies, didn't drive, we locked everything down, and still only saved about 8%. So that's conservation isn't going to get us a huge amount of savings. We're just going to have to change our efficiencies and the way we distribute things. So some of the largest savings in terms of efficiency is in load leveling. So this is the whole power grid. So think about a big city, and even in Huntsville, what happens in the morning. So from midnight to 6 a.m., not a lot happens. And so we have a drop in demand. So this black curve is demand. And so we need to be able to sort of scale back our use of primary fuel in generating electricity when demand drops. But coal, nuclear, hydroelectric, well, hydroelectric may be easy to do, but these first two, um, all three of these, hard to stop and start. Whereas natural gas, very easy. So that's why Roans Prairie exists. If you go towards College Station, you see that power station at Roans Prairie. That is a natural gas turbine. And so it's basically like a jet airplane engine that runs on natural gas. And so they can turn that engine on and start generating electricity really rapidly. So when people start waking up, their alarms go off, their heating profiles kick on so they can heat the house or cool it down depending on summer or winter. They get the curling irons out and everything and start really using a lot of electricity. They can turn on those natural gas turbines, and they can meet demand without changing the base electrical load. So that's very good because we can then run our base electrical load at its peak efficiency. So they can turn the heats up just right and have it all running perfectly and let it go, so that it's just constantly generating the most efficient amount of electricity per joule of input, and use natural gas and other things to level the load. Now, there are other things other than natural gas. This would be where battery backups to wind or battery backups to solar would play a role. So we could start drawing on those battery storage mediums that have collected their energy from wind and solar. And so let's look at all those things. So what is the typical customer usage? Monthly usage is about 1,000 kilowatt hours according to Entergy. And so how much power is that, and how many amps? Because if you're buying solar cells, you need to determine how many watts you need to generate. And so we need to convert kilowatt hours to kilowatts. So if you're running for a month, let's say a month is 30 days, and 24 hours in a day. So what we're doing is we're sort of canceling that hour part. It's a kilowatt hour per month. And so we want to cancel the months, we're going to cancel the days, and then we cancel the hours. And this is how many kilowatts we have. So that would be the average power over the whole month for your house. Now, that's not That's not a lot. And there's going to be times when it peaks above that and times when it drops below that. And then also converting that to amps. If we just are running everything on 120 volts, which really isn't accurate because your dryer and your heater and so on might run at 240, but still, this would be about an average over the whole month of 11 amps, which is not a lot of current. But if you look at your breaker box, like on the back of my house, about a 2,000 square foot house, it has a 100 amp breaker box. So that would be the maximum current that could come into my house. So 100 amps at 120 volts would be 12 kilowatts. So if I wanted to turn every circuit on its max, then I would need like 12 kilowatts of power, solar or wind or whatever. That's a huge amount. They say the typical power rating would be, a peak power rating would be 3 kilowatts. So this is probably what you want to aim for if you're going to try to put your home on an alternate energy source, is to aim for 3 kilowatts, maybe a little more to give you some breathing room. If you want to know what the minimum power is in your house, you can go out and you can write down the meter reading, and then turn everything off and leave your fridge in, your water heater, all of those things that you have just their base load, and then wait an hour and then write it down, and then you take the difference, and that's how many kilowatt hours your fridge and things take. Okay, so this idea of this energy spectrum, we need to think about the speed at which we pull the energy out. And so we're going to talk about these two. Probably the slowest would be these hydroelectric storage media. So if we want to store a large amount of energy, but have a high impedance, meaning it's slow to pull out, then this something like this pumped hydro reservoir would be. So you've got a hydroelectric dam, and the load drops, the demand drops, I should say, then they can start pumping this water uphill into this reservoir, okay, and reduce the flow through the dam. And so you're sort of storing that until later, and then later you can let that water come down out of the reservoir and generate electricity from that. So when demand goes back up, you start letting the water flow back out. But that's going to be slow, but it's going to store an enormous amount of energy, but it's slow to get to. Some of the fastest energy storage, so high power, would be these uninterruptible power supplies, and these are these little cylinders. They look like this one. This one is apparently for a spacecraft. It's a NASA. So they would take, like on a spacecraft or the space station, you have the solar cells, and they're storing electricity into this flywheel storage. So inside here is something that's spinning really fast. And then when you need a burst of current, you latch into that with an electric generator, and it generates current. So I put the little pieces of those efficiency charts in here, so they're not in your notes, but you can kind of see this is that pumped hydro. Down here is the electric motor flywheel. So when we want to store electricity, we spin a flywheel, and so we have the mechanical energy of the flywheel spinning. And then later, when we want to pull that electricity back out, we hook it into a generator and generate the electricity with the stored kinetic energy. This is that energy spectrum where if you can store it for 10 hours or more, then that's what we call commodity storage, like the pumped hydroelectric. We're storing it up in a reservoir, can store it for months and months and months. If we only want to store it for seconds or even milliseconds, that would be like capacitors. And so you see those in your electronic devices. A lot of times the power cable comes in and it's hooked to a little DC converter, and there's a capacitor there. So like if you unplug it, it doesn't shut the whole thing down right away. You can unplug it, or there's a blink in the power. It doesn't shut your computer down. There's a capacitor in there that will hold enough charge to keep it going through that dip. That's also what we call transmission stability. So these little dips and so on are smoothed out by these capacitors. And so let's go through the chemical storage. So redox reactions. These are batteries, but think about a battery. It's not very convenient because you have to change them out. Wouldn't it be nice if you had a battery that was continuously regenerated? And so that's what these are. They're called flow cells. So this is a fuel cell or a flow cell or a flow battery, a bunch of different ways of describing it. And this one is a sulfide bromide cell. So you can see the two reactions here. You have sodium sulfide on the left, changing the amount of sulfur is attached to and producing sodium ions, which are then transferred over to the other side that react with the sodium bromide and change the number of bromines that are attached. And so the sodium ion is a pretty small ion, and the current going through this permeable membrane, this ion selective membrane, is the thing that limits the current of this battery. And we can conduct sodium ions pretty fast. Lithium ions we can conduct a little faster, but this would be a really good high power battery setup. Okay. Yes?
How small can they be?
I'm not sure. A lot of these are made for like storing the electricity from windmills or solar cells, and so they're not small. And this one, I'm not so sure about the sodium sulfide or sodium bromide in terms of its toxicity, but some of the others you definitely wouldn't want to be like human portable. Like this next one I call, the vanadium. Let's go to this one. I want to try the sodium sulfide battery. This one scares me actually because molten sodium, which will generate hydrogen upon contact with water, okay, and molten sulfur. So I call this the fire and brimstone battery. You know, you see in the biblical stories, fire and brimstone rain down out of heaven. And so the brimstone, that is sulfur, burning sulfur. And I had an experience with this, not a biblical situation, but my high school teacher left on maternity leave. She was my favorite. She's the reason I'm a chemist, probably, Mrs. Blackman. and she was replaced by Mr. Dom, who was even my parents' chemistry teacher, like when they were in high school. Yeah, and he had this purple mimeograph sheet. Have y'all even seen a mimeograph sheet? It was a fast way to make copies before they had the Xerox machines and the toner. And it had this purple ink, and you made a master. I don't remember how they made the master, but you put it on this thing, and it had this solution in it, and it would basically make a copy with purple ink. I don't know what the deal was with the purple ink, but you got these purple sheets. And he gave us this lab where we were supposed to react copper with sulfur. And so you take a copper wire and you put it in powdered sulfur, put it in a crucible, and catch it on fire, or melt the sulfur over a Bunsen burner. But the gases almost always caught fire, and so you made sulfur dioxide in the lab. This brown gas is pouring out of these crucibles. And at the bottom of the mimeograph sheet, it said, under no circumstances is this lab to be done outside the hood. And in my high school, we had like 6 lab benches with this boiling sulfur in the lab, and all of us were at the window, like gagging. He was like, bunch of pansies, turn off the fires, leave. Like he dismissed us from lab, but we were like, please let us, we're dying, And it was the worst smell. It was one of those things that your body just rejects. So when I see this particular battery, it's super efficient though. That's the problem. So 89% efficient. You put in 100 joules, you get 89 out. Yeah, that's great. And it's probably high current. We're conducting sodium ions. And it's pretty simple construction. You can put an electrode in both. You have a can that the sulfur's in. You have an electrode where the sodium is. And so this has already been deployed in several places with large power ratings. For deploying like with solar or wind, where you have intermittent power. So the intermittent power charges up the batteries, and then the batteries are not intermittent. So in all of these situations, we're limited in solar and wind because we need to condition that power. It fluctuates. And so we need to take that fluctuation and install some sort of flow battery system so that we can run our solar power at night, right? So you charge those batteries up, and then at night when you want your air conditioner to come on, you got to have power. And so they go hand in hand. Without good battery technology, we really can't utilize solar or wind. That's the take-home lesson. There's some other kinds of batteries. The vanadium cell, which can be 85% efficient. I'll just kind of shoot through these because there's really not that much difference between them. This is a zinc bromide cell developed in the 70s, 75% efficient. This one's kind of cool. The military commercialized this, and they have it in like an 18-wheeler Connex. Here's 4 of these cells in one of those 18-wheeler containers that they could bring into a theater, drop down, and generate electricity with this, and then charge it up. Here's the old just the old reliable lead acid battery. And so it just we know that they can be recharged and discharged, and so they just built a whole building full. So this is in California. You can see this whole building is full of lead acid batteries. Then lithium-ion batteries. This is the one you're most familiar with, and it's very close to 100% efficient. So you put in 100 joules, you get 100 out. It's got a pretty long life cycle, 3,000 cycles at 80% depth of discharge. And so this is what is in your phones, your laptops, and so on. And it's nice because they've now come up with some standard shapes. The 16, 8, 30, I can't remember the number, but it's like a 5-digit number of the cell type, and it's bigger than a AA. And so it's about, it's a battery that's about that long, and about that big around. So that's the size, the standard lithium-ion cell. And so you can see those being used in lots of applications because they're so rechargeable, and they're standard size now. So. And then there's metal air batteries, which is kind of interesting. This is a zinc reacting with oxygen. We know that's a very exothermic and spontaneous reaction. And the nice thing about this is that you don't have to create or carry around your oxidant. It's just air. So this battery actually breathes. And so when you charge it, it releases oxygen, and when you discharge it, it consumes oxygen. And so this is kind of an interesting battery. You know, you're only really paying for one of the electrodes, so the other component is oxygen. And then we have supercapacitors. So this is really not an electrochemical reaction, it's just storing charge. So because there's really no need for a cation transmitting membrane, this can be the fastest current available. So if you think about that, all of the batteries have to conduct cations in the battery in some sort, lithium, sodium, hydrogen ions, and so on. So that's the current limiting step. We can stuff electrons through a wire at really high currents. The thicker the wire, the faster you can throw electrons around it. Now, the electrons hate each other, so they travel around the surface of the wire. So that's why high current wires, if you go to Home Depot, they're thicker. They can just carry more electrons. It's like a 6-lane highway versus a 2-lane road. Okay. But inside the battery, we have to conduct the positive charges, except for a capacitor. For capacitor, we're just basically taking the wire system and we're stuffing the electrons on one side of it. And what happens if you steal electrons from the left side and put them on the right side? The left side is really positive. But we haven't moved any positive charges. You see how simple that is? The problem is the breakdown voltage in between. If you get enough of a voltage, then the material between will break down and those electrons will shoot across the gap and short out. And so the electrode shape, the electrolyte in between, it's going to keep those charges apart. Not electrolyte, dielectric. The thing that can handle the charge is where the research is. So we have some pretty good supercapacitors. These would be what you would have in like an electric vehicle, where you charge your battery with either the charging station or with an electric motor, like in a hybrid. So you've got your battery charged. The battery has impedance, right? It's resistant to deliver its current. And so also in that chain, you have these capacitors. So when you step on the accelerator and you need torque, torque is related to the amount of magnetic field you generate in the motor. And so you need current to generate that magnetic field. So you need high current to get started, but you don't need high current to keep going. So in order to start an electric motor, you need high current. So you need those supercapacitors. So we have batteries and supercapacitors for the really high current situations. And then once you get going, then you can charge those capacitors back up and be ready for the next time you need to start. So these are fantastic. I don't really have a spot for them on my efficiency diagram. So I just put them between electrical and chemical, but it's really not chemical. We're not doing any chemical reactions. And so in that efficiency diagram, I don't have a place for capacitors. Yeah, so I don't exactly know where they fit because we're not doing chemical reactions. This is also, in a large aspect, kind of how our power grid works. Think about what's happening at the power plant. We're spinning this electrical generator, and it's charging up the power lines. The way we originally decided to track charge was positive charges. You know, physicists went early on, they're exploring electricity, and they decided to define current as the flow of positive charge. But the positive charges aren't really flowing, except like internally in a battery. It's the electrons. And so what the power plant's doing is sucking electrons off the wire. So you got those long wires, and this generator is just pumping electrons off that wire and sticking them into the earth. And the earth is acting like this giant negative electrode on the capacitor. And so all we have to do at our house is connect this positive electrical line to our circuit, and it's grounded to the earth. And so then the electrons will come out of the earth, flow through our circuit to get back on the power line so that they can be sucked out by the power plant. So that's what's going on with our electrical grids. Kind of strange, but it's like a giant capacitor. So those power lines are really, really positive, and the earth is ground, and it has lots of electrons to donate. So this is compressed air energy storage. So this is very similar to that that gravity storage, only instead of gravity, we're stuffing air down into, say, a limestone cavern. And so if we have our power plant that's generating electricity during the day, it's running at peak efficiency, but then demand drops, then the power plant stops generating electricity. So it stops spinning the generator and starts spinning this compressor, and it compresses air down into this cavern. And so in midnight to 6 a.m., it's generating pressure in that cavern. And then at 6 a.m., all of the air conditioners kick on to get the buildings comfortable for the next day. And it starts pulling air out and running that generator again, in addition to its regular load. And so it's just giving, again, more force on that turbine, generating electricity. So it's again, acting like a capacitor, but this time with pressure. Here's the pumped hydro, an actual picture of one. This is nice. This is an 75 to 85 or 70 to 85% efficiency range. So look how much higher this is. So we're getting electricity out of this drop right here in terms of that river. And I mean, you're standing by that dam. It looks like a pretty tall dam. But then way up here on the top of this mini mountain, we got this huge reservoir. This is a little lossy though, because it's got that huge surface. You could lose water. And so what they need to do is come in here with the same thing we have in our lab when we're heating water, is put the polystyrene beads in here, or polypropylene beads. So we have these little beads that we put on the top to basically put a cap on there that's flexible and to reduce the opportunity for water to escape. So this is high energy storage, very low power perhaps. And here's the highest power storage, this kinetic energy flywheel. And it can be up to 90% efficient. So remember the sodium sulfur battery was 90% efficient. But I like this a lot better because there's no sodium involved, no liquid sodium. It doesn't have to operate at 300 degrees C. There's no sulfur. It's not going to kill me unless I somehow get involved in the spinning thing and it breaks apart. I guess it could be dangerous, but it's not chemically dangerous. So this is they pull a vacuum in here, so there's no air currents, and they have this spinning thing, this heavy thing that spins, and that stores the mechanical energy. And there's no friction because they have magnetic bearings. And so the north-south magnets on the container and the little rim are opposite each other. And so it's suspended between a magnetic field. You spin it up with electricity. And then when you need to pull the power out, you clutch in the generator and it generates electricity. So you can put these things, I guess you could buy these for your house. Your power goes out, then clutch in and start pulling electricity off the grid. It would be great for leveling solar, so you just charge it up during the day and consume it at night. Right now you can buy whole house solar systems that come with a whole house battery, a Tesla battery that you can put on your house and run your house on that battery at night and then charge it up during the day with solar. But this would be one that's probably going to last longer than that. So this is sort of a survey of all of the different systems we have. So just the terminology I want to emphasize again. So power applications would be fast. But by power, we mean fast, kilowatts. Okay. And energy applications are slow and large storage. So like the batteries, they don't have a lot of storage capacity, flywheels and so on, but they're fast. Energy, again, large storage like pumped hydro, compressed air, certain flow batteries, you know, you can store a large amount of energy in those, but they're slow. Here's one that doesn't even have an arrow on my diagram, which is a little strange. So this is going from light. This is going from light straight over to thermal. So we're just using the sun to heat up steam. So that's pretty cool. These are parabolic reflectors, and they have probably quartz tubes that run along so they can get really hot. And the sunlight is focused on those tubes and heating up the water, boiling it, and then heating up the steam. And so then it goes and spins a turbine. So that's pretty cool. But look at the footprint. It's huge. That's a lot of land, okay? And it's only generating 354 megawatts. Now that's 354 million watts. That sounds like a lot. But if you look at this road here, let's go with maybe this road right here in between these two power plants. There's a road right there. It's on the same scale as this road here. And this footprint is, 590 megawatts, 590 and 445 megawatts in terms of the same footprint. So this footprint generates more than 3 times the power that this steam plant does in terms of the footprint. Now in thinking about this, I realized it's not exactly apples to apples because you got to get the coal from somewhere. And so if you include the Powder Basin of Wyoming or Green River, Wyoming, where they mine the coal and bring it down to LaGrange, there's a huge footprint up there where they've essentially taken the side of a mountain that has a lot of coal in it and blown it up with explosives and sucked the coal out. And so there's a huge impact there. So what you would need to do is then compare the costs, the land values and so on to make that decision. The real difficult one from a land use area. So if we're going to use this uninhabited area for coal mining, we destroy the hill basically. They reclaim it. Like if you see up near Rockdale, we have some coal mines in Texas. They've reclaimed that area. It's gorgeous. They covered the pit with topsoil. There's water there. There's deer. There's trees and everything. So that's a brand new sort of reclaimed area after they've mined the coal. So it's not like they leave a smoking pit of coal residue. Most of these things have an environmental plan, and when we're done, we restore the topsoil and plant grass and so on. But photovoltaics, because the transmission of electricity is not is a problem, in getting it to market. This is the footprint for a photovoltaic one in Germany, and this is only 40 megawatts. Look how huge it is compared to this power plant. And it has to be pretty close to the area where the electricity is going to be used. And so if it's near a populated area, the property value that's consumed by this is enormous. So it would be, hundreds and hundreds and hundreds of millions of dollars, maybe up to $1 billion of property value if we were to put this in northern Houston, like by the airport. Okay. Whereas the power plant for nuclear or coal or natural gas is a much smaller footprint near the residential area. And then the primary area where you get that energy, whether it be coal or in the ground, natural gas, those don't have any impact on the property area. So they're much easier to implement. Looking at photovoltaics, you can go to this National Renewable Energy Laboratory, and they have a lot of calculators for your home. So if you're going to go solar, you can go there and you can see in your area how much power you could generate per year. This would be for a 25 square meter array. I could get 5,600 kilowatt hours per year in the Huntsville area. That's a huge array though. The old rules of thumb, and so here's for the homework, use these rules of thumb for your calculations of $8 a watt and 10 watts per square foot. Now, things have improved greatly since then. So I had Thomas, I was telling Thomas these numbers because he got interested, my son Thomas, interested in solar. And when I told him $8 a watt, he scoffed. He said, no, it's not that anymore. And so now it's getting down to around $1.50 a watt. That's fantastic. Now it's starting to become feasible to power your home with solar. You still have a problem with the storage during the nighttime. Okay, so it's not going to solve your whole problem. If you really want to go off the grid, that's expensive. But just adding solar to your house, and I think really makes sense to have solar added to your house just because of air conditioning costs. When do we need extra power? In August, right? It's to air condition the home and to heat your home in the winter. So in those times when the sun is out, you can supplement your power needs. Now 3,000 watts per home is around 4,000. Using the rule of thumb numbers from the previous page, it was much more expensive. And so this is just some cost analysis showing that really the cost of the hardware is what's really made the difference. Labor hasn't changed that much. And then lastly, the radiothermal battery. This is a plutonium-238. Look at it. It's not painted red. That's how hot it is. But if you want a substantial amount of power, thermocouples only generate 7%, so 7 joules out of 100. But if you don't ever want the power to go out, this is a very stable source of energy, because that plutonium-238 is going to be hot for centuries. So this is what we put on our satellites. It's only 7% efficient. It's radioactive as hell, but you're not going to be by it. So you send it up into space and it's going to generate electricity for centuries, which is cool. You don't ever have to change the battery. You don't even need the sun. And so that's really neat. Just if we could make this more efficient, we could just make radiothermal batteries down below the city where nobody's there, nobody cares. I'd hate for it to leak, but again, it would just generate electricity for centuries. And then lightning. We've never figured out how to use lightning. It's everywhere. We see it all the time. And some of these lightning strikes generate 6,000 megawatts, but for 1 millisecond. But if we could capture it and hold on to it, then that would be really great. So here's some sources you can look for more information.